So in order to use Taylor polynomials effectively, we will use Taylor's theorem to estimate the size of the error. The remainder given in the theorem is called the Lagrange form of the remainder, or the Lagrange error bound. This gives us a bound for the error, not the exact value of the error. So if a function f is differentiable through order n plus 1 in an interval containing c, then for each x in the interval, there exists a number a between x and c, such that f of x is equivalent to, this would be our first term of the Taylor polynomial, this would be our second term of the Taylor polynomial, or at 0, at 1, this would be our third term, and dot, 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 all the way to our nth term, and then whatever left over is the remainder. So that's down here. That's your remainder. So what we're going to do is we're going to call this from here all the way to here. We're going to call that the approximation part. And then we're going to call this what is left over, because it's almost like you truncate it. So you take your, whatever the nth degree is, that degree, Taylor polynomial, and then this remainder is going to be equivalent to this down here. So you can see that it is the n plus first derivative at a divided by n plus 1 factorial times x minus c to the n plus 1. So it's just that next term in your Taylor polynomial. And your a is going to end up being the maximum. So this is the n plus first derivative at the maximum. Okay, so n plus first derivative at the maximum. Okay, and we're going to call that whole thing capital M at our next page here. So let's just wait for that. So okay, instead of finding the exact error of our approximations, we will use two rules that will help us find an upper bound for the error. In this way, we will know the most that our approximation is off the actual mark. So if the series is an alternating series, the error will be no greater than the absolute value of the first unused term. Okay, and we talked about that on I think, lesson 4 or 5, I can't remember, one of those videos. And if a non-alternating series is approximated, we will use Taylor's inequality theorem, which is otherwise known as the Lagrange form of the remainder. So this is the Lagrange form of the remainder. So the absolute value of the remainder is less than or equal to, there's our maximum that I was telling you about. Notice that that m is equivalent to our n plus first derivative at a. Okay, that's going to be your maximum. So m is for maximum, is defined to be the maximum value of the n plus first derivative at a, where a is between x and c. And notice that the rest of this is just that next term of the Taylor polynomial. So the n plus first term. And so we're going to use this to find our Lagrange error bounds. And what we'll do is, once we find that error, we will add that error to our approximation, and then we'll subtract it from our approximation, and that will be our bound. So for n equals 0, Taylor's theorem states that if f is differentiable in an interval containing c, then for each x in the interval there exists a between x and c such that f of x equals f of c plus f prime of a times x minus c, or f prime of a equals f of x minus f of c over x minus c. Do you recognize this as the mean value theorem? So now, vocabulary check for understanding. M represents the maximum absolute value of the n plus 1 order derivative. So the maximum value of the n plus first order derivative on the interval between c and x. We can find m by substituting the a value between x and c that maximizes the expression, absolute value of the n plus first derivative at a. So whichever number maximizes it. So the expression, absolute value of x minus c to the n plus first over n plus 1 factorial, represents the first unused term n plus 1 in the Taylor series. And the product, absolute value of x minus c to the n plus 1 over n plus 1 factorial times the max of, and this doesn't mean the max times it, it means the max of the n plus first derivative at a. So, you're going to be looking at the n plus first derivative, and you're going to pick that a where the maximum lies. And you're going to take that maximum and multiply it by the x minus c to the n plus 1 over n plus 1 factorial. Will tell us a safe upper bound. For n plus 1 derivative at x equals a. So if the max of the n plus first derivative at a on the interval between the center c and the value x equals a is not given or easily found, then choose the first known reasonable number greater than this absolute value of the n plus first derivative at a. If you don't know the maximum or the interval, assume the interval is from the center, which is what, the c, the center, what you're centering your Taylor polynomial on, to the x value you are using. Two facts about the error, or r sub n of x. First, if we increase n by adding more terms to the polynomial, the remainder will decrease in size. Second, as we move away from the center of the polynomial, the size of the remainder will usually increase. So you want to be close to where you're centering it. That is for sure. Okay, example number 1. The function f has continuous derivatives for all real numbers x. Assume that f of 3 is 5, f prime of 3 is 2, f double prime of 3 is -4, and f triple prime of 3 is 7. Write a third degree Taylor polynomial for f about x equals 3 and use it to approximate f of 3.2. Give 3 decimal places. So I'm just going to call it polynomial sub 3 of x. And I know that my f of 3 is 5 plus my f prime of 3 is 2 times x minus 3. And you could put it over 1 factorial if you want to. Plus, my f double prime is negative 4 times x minus 3 to the second over 2 factorial. Plus, my f triple prime is 7 times x minus 3 to the third over 3 factorial. And so that is my third degree Taylor polynomial. And we're going to now use that to approximate our f of 3.2. Okay, so it's approximately equal to my p of 3.2, which equals 5 plus 2 times, now this, if I put my 3.2 minus 3 in, I get 0.2, minus, now 4 divided by 2 is 2. So I basically just took negative 4 divided by 2 factorial, which is going to give me negative 2. And then when I put my 3.2 in, I get 0.2 to the second. And then I have 7 6, because 3 times 2 times 1 is 6. So 7 over 3 factorial is 7 6. And this would be 0.2 to the third power. And now I want you to put this into your calculator, and you can pause the video for a second. .329. They said give 3 decimal places. And so that was that. So part B, the fourth derivative of f satisfies the inequality. F, fourth derivative of a, the absolute value is less than or equal to 35. So that's giving you that 35 is your maximum. That's your m for all x in the interval from 3 to 3.2. Use this information to find a bound for the error found in A. So the absolute value of that remainder, sub 3 of x, is equal to the absolute value of f, the fourth derivative, at A, times x minus 3 to the fourth over 4 factorial. And remember, we said that this right here is your capital M, right? And we also said that this is less than, if we put our capital M in, and we put, well, I'm just going to put the capital M in this first time, on that interval from 3 to 3.2. And so now, if we say, okay, we want to use this to find our remainder, which would be our error, when we're using our Taylor polynomial to calculate 3.2, it's going to be less than or equal to, this is going to be 35 times, and when I put my 3.2 in, I get 3.2 minus 3 is 0.2 to the fourth power over 4 factorial. And please pause the video and put this in your calculator to give me an answer. And you should have gotten 0.00233. Find an interval AB such that f of 3.2 is between A and B. So what we would do is we would take our 5.329 and we would subtract our 0.00 Goodness, I'm so sorry. Is contained on the interval 5.327, 5.332. Can f of 3.2 equal 5.334? And the answer to that would be no. 5.334 is not contained in the interval. And so for our example number 2, estimate the sine of 0.5 using a Maclaurin polynomial. What is the least degree of the polynomial that assures an error smaller than 0.001? So there's 2 different ways you could approach this problem. One way is that you could start with your remainder. You really don't know what our n is. That's actually what we're trying to figure out. But we know that it's going to be less than or equal to, and one thing that you need to know for this is, and this might come in handy for any time you're doing an error. We know that for sine and cosine, the absolute value of sine x has to be less than or equal to 1. And the absolute value of cosine x has to be less than or equal to 1. So if you're trying to find the maximum m, it's going to be 1, right? That maximum is going to be 1 if you have sine or cosine. And we are actually using sine. So we know that if we were doing like m times the n plus first derivative, our m is going to be 1 times our n plus first derivative at 0, using our 0.5 divided by, because this is our Maclaurin, so that is centered at 0, at x equals 0. So our x minus c is going to be 0.5 minus 0, because our center, our c is 0. So that x minus c is what I have right here. That is your x minus c. And this is our m. So we know that our error is going to be less than or equal to that n plus first term. And we want it to be less than or equal to 0.001. Oh, it said smaller, so I guess no equal to, okay? And so doing that, you're going to say, well, I'm just going to try different n's. So if n is 1, and then you're going to, put your, this is what we're going to be calculating. This is going to be 0.5 squared over 2 factorial. And so if you put that in your calculator, you should get 0.125. If n is 2, you're going to have 0.5 to the third over 3 factorial. And put that in your calculator, 0.02083. If n equals 3, you have 0.5 to the 4 over 4 factorial. That's going to be 0.00260. What if n is 4? 0.5 to the 5th divided by 5 factorial, which gives you 0.00026. So the first one that actually that you actually see is less than 0.001 is this one, okay? This one still wasn't, so this one isn't, this one isn't, this one isn't. This is the first one that is. And so that tells us that n equals 4. I'm going to say, therefore, n equals 4 is the least degree such that the absolute value, so then of r sub 4, 0.5, is less than 0.001. Okay, that was one way to do the problem. The other way that we could do the problem, I'll do it in orange, is if you remembered what your sine x was equivalent to. And our sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, 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 okay? And if we if we wanted to calculate our sine of 0.5, we would say, okay, 0.5 minus, then we would do 0.5 to the 3rd over 3 factorial, and then we would do plus 0.5 to the 5th over 5 factorial, and I might stop there and then just put these values in my calculator. This one gives me 0.02083, and then this one gives me 0.00026, and this one that I just spotted is the first one that is less than 0.001. And so this is considered your, it's to the 5th power. So if the 5th degree is the error, right? If this is the 5th degree, that's your error, then that means that n is 4, is your least. So again, you would have said that n equals 4 is the least degree such that the absolute value of the remainder at 4, which would be your 5th term, is less than 0.001. So either way, you're getting that same answer, okay? All right, so example number 3. Let p sub 3 of x be the 3rd degree Maclaurin polynomial for f. Using information from the graph of y equals the absolute value of the 4th derivative at x, shown below, show that the absolute value of p sub 3 of 1/4 minus f of 1/4 is less than 1 over 400. So, if you remember what your e of x is equivalent to, you could quickly figure it out that every time you take a derivative, you stay with e to the x. But your Taylor polynomial as a summation is x to the n over n factorial, that summation from n equals 0 to infinity. And so if you wanted to think about it, you're like, well, ooh, sorry. I accidentally looked at, goodness, sorry. This isn't e to the x. This is, the next one is e to the x. So sorry. I looked down and started working the wrong example. For this one, your remainder sub 3 of 1/4 is less than or equal to the absolute value. Now, we have to find the maximum. I need to find my m. and it's a Maclaurin polynomial. It's centered at x equals 0 when it's a Maclaurin. And so when I go to 0 and I know that what I'm trying to, oh, I just saw that this is 1. What I'm trying to find out here is, so this would be 1/4. So here, this is the point on my fourth derivative. My fourth derivative, I've got 1/4 10, and this looks like about 0.15. So remember, you are trying to find your maximum here. So I'm thinking that your maximum, according to this graph, is going to be at 0, is going to be 15. So when I'm trying to write my, use my Lagrange error, I need my m, and then since this is 3 here, this is going to be 4 factorial, so m over 4 factorial times, and then our x minus c to the 4th power, right? And our x value that we're trying to approximate is 1/4. Our c, it was centered at 0. And so we want this to be less than 1/400. So now I'm just going to start simplifying this right here. So to do that, I'm going to write it as my 15 is 5 times 3. My 4 factorial is 4 times 3 times 2 times 1, I guess. And then this would be times 1/4. So again, I've got, oh, but 1/4 to the 4th power. So this would be 4 to the 4th in the denominator. I'm not going to worry about the 1 to the 4th. I mean, if you wanted to write it, it's fine, but we don't need to worry about it. And we're trying to see, you know, is this less than 1/400? That's what we're hoping, you know, because that's what we need. And so 3's cancel. This gives me 5 over 2 times 4 to the 5th. And again, we're trying to figure out, is it less than 1/400? So now we're going to use the calculator. So go ahead and pause the video and let's see if you can get these same values that I'm getting. 0.00244 is less than 0.0025. And yes, that's true. The 0024 is less than 0025. And so since I find out that that's true, therefore the absolute value of r sub 3 of 1/4 is less than 1/400. And they wanted us to show that. So that's what we just did. And the cool part about that problem was that you had to figure out your m. And remember, you're just looking for the highest y value in that area. You know, this was your c was 0, your x was 1/4, and so when you find it in between there, the one that ended up being the highest value in between here and here was 15, and that happened to be at x equals c, which was x equals 0. So, you know, in between this interval, what is the highest of the function that is your fourth derivative? Okay, so that one was good. That was a good one. Now we can do the one that I thought I was on. And just here it says, note, if an error calculation is required on the AP exam, all work must be shown so that calculator can only be used as a method to check your computations. So make sure you don't just write a number here, because they will not give you points for that. You might get 1 point if you got it right, but you could get more points and still get the answer wrong if you show your work. So use the Maclaurin series for y equals e to the x to estimate 1 over the square root of e accurate to 4 decimal places. And the first thing I did on this one was I said, oh, this is e to the -1/2. Because of course we're using e to the x So I wanted to find out like what my I'm really trying to find f of negative 1/2, right? Because that would be e to the negative 1/2. And accurate to 4 decimal places, meaning that we would use the calculator to see what this exact amount is with the calculator, or, as exact as possible. And then we are going to find what degree we would have to take this to get something that was the exact same for 4 decimal places, okay? So if you did not remember how to do your Taylor polynomial and you wanted to just quickly, try and do this, look, every single derivative is e to the x. So you should quickly see, and it's Maclaurin, so now you're finding y of 0, which is 1. And then look, y prime of 0 is 1. So not only is every derivative e to the x, every derivative's value at the center, or we're centering it at 0, is going to be 1. So if I was, trying to figure out my Taylor polynomial, it would be, y of 0, and then I would say plus my y prime of 1 times x, well, just be times x, because it's x minus 0, plus our y double prime times x squared over 2 factorial, plus 1 times x to the 3rd power over 3 factorial, plus dot, dot, dot. Okay, so, and if you wanted to write this as a summation, our e to the x is equal to the summation. We could say n equals 0 to infinity, because we want the first one to be 1, and we could say x to the n over n factorial, because 0 factorial is 1, so that'd be 1 over 1. And then if n is 1, 1 factorial is 1, so that would just be x. And then when n is 2, it'd be 2 over 2 factorial, so that actually would work. And so this is our summation. So we created a Taylor polynomial, and we created the summation equivalency for e to the x. And what we need to find out is we need to find out a k value such that, and remember, oh, well, I was going to say that the maximum error, since this is an alternating series, we would be using our negative 1/2 to the k over k factorial. That's going to be our error, and so we want that to be less than 0.0001. Okay, so this is the maximum error, since it is an alternating series. And so our error, our absolute value of our error, is going to be less than or equal to our first unused term. And so since we're trying to find it at negative 1/2, this is like our x, and then we know it's going to be some power and then over some factorial, that same factorial's power. And so this k should be my n plus 1. Okay, so now I just kind of started calculating, I think I calculated like p to the 5th of negative 1/2. And so using my p to the n, I of course get 1 for the first one. I get negative 1/2 for the second one. I get 1/4 divided by 2, which is 1/8 for the third one. I get negative 1/8 times 6, so negative 1/48. The next one would have been positive 1/16 times 4 factorial. So I'm just going to write it like that. So 1, 2, 3, 4, 5. That's 5 places. And so I took my calculator, negative 0.5, and I just started, you know, like, I think I actually, now that I'm looking at it, I did this 32 and then 5 factorial. I did that one also. And just started looking at all the different values. And I saw, I'm going to go ahead and kind of let you investigate that. And then you should see that your remainder ends up being negative 1/2 to the 6th power over 6 factorial. And the reason why is because that's equal to 0.1, 2, 3, 4. 4 zeros. That's the first time that you get that, because so that ends up being your K. And so your actual value, your exact value, well, I mean, you had to round it, so we can put an equal sign like that, is 0.6065306. And your P sub 5 of negative 1/2, if I put all of those in my calculator that I just calculated here, it gives me 0.6065104. So you can see that they are exactly the same for 4 places behind the decimal point, okay, which is what they asked for. 4 places, 4 decimal places. They're exactly the same. And so it ended up being a 5th degree that gave it to us. All right. Last page. Using the Maclaurin series for cosine x, write the 4th degree polynomial and use it to compute the cosine of pi over 12. So the one thing you need to memorize is these the cosine and sine equivalencies for Taylor polynomials, or Maclaurins, I'm sorry, Maclaurins. And the cosine is summation from n equals 0 to infinity of negative 1 to the n times x to the 2n divided by 2n factorial. So that you just need to memorize. I mean, you could produce it, but it's kind of easy to memorize, and I think that that would help you. So if I had to sit down and say, okay, what about when n equals 0? Okay, that's going to give you 1. What about when n equals 1? Well, that's going to give you negative x squared over 2 factorial. What about when n equals 2? That's going to give you x to the 4th over 4 factorial. And so this is the 4th degree. Even though it only has 3 terms, it takes it to the 4th power. And so we're going to say the cosine of pi over 12 is equivalent to, and we're going to say 1 minus, and this is going to be pi over 12 squared divided by 2 factorial plus pi over 12 to the 4th power divided by 4 factorial. And so if we put this in our calculator, this will give us 0.9659262729119, and yours might not go that far. And then in my calculator, I'm going to calculate the value of cosine pi over 12. Make sure you're in radians. And that is going to be 0.965925826. And so you're going to say, well, wait, 96592. They're both exactly the same for 0.96592. So for 5 places behind the decimal point, you are exactly the same. And then it says, use the Lagrange error bound to show that the absolute value of f of pi over 12 minus the Taylor polynomial at pi over 12 is less than or equal to 1 over 5,000. So remember that your absolute value of f of pi over 12 minus p sub 4 of pi over 12 is less than or equal to the absolute value of the maximum. And since we went to the 4th power here, it would be over 5 factorial times x minus 0 to the 5th. And so this is a cosine function. Your maximum is going to be 1. And so we're going to say, okay, your remainder sub 4 will be less than or equal to 1 over 5 factorial times pi over 12 to the 5th. And so put that in your calculator, and that actually equals 0.123410248. And so now you're saying, okay, is this less than, we're going to say, question mark, less than or equal to 1 over 5,000. And so if I put this in my calculator, 1 over 5,000 gives me 0.0002. And so I'm comparing this, and this is true. And so I guess you can say, therefore, that, therefore, the absolute value of f of pi over 12 minus p sub 4 of pi over 12 is less than or equal to 1 over 5,000. All right, so part C, use the 4th degree Taylor polynomial for cosine x and, about x equals 0 to find an approximation for a cosine of 0.8 and determine the accuracy of the approximation. So again, we can write cosine x equals summation from n equals 0 to infinity, negative 1 to the n times x to the 2n divided by 2n factorial. And so this is going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And now we look at the cosine of 0.8 as being equivalent to 1 minus 0.8 squared over 2 factorial plus 0.8 to the 4th over 4 factorial, which is approximately 0.6970666. And so our error is less than or equal to the absolute value of our next term. And so we're going to go and we're going to say, okay, the absolute value of cosine 0.5 minus the Taylor polynomial sub 4 of 0.8 is going to be less than or equal to, and we've got our m to be 1 times our 0.8 minus 0, which is just 0.8, to the 6th power over 6 factorial, because our next term would have been 6. And that is approximately 0.000364088. And so, the accuracy of our approximation should be good for 3 places behind the decimal point, because however many zeros you have here, that means that it will be good for that many places behind the decimal point. So 0.697, they're going to be exactly the same because of our error, okay? So 0.697. And then find the interval such that, you know, the cosine of 0.8 lies between those two values. So we've got our 0.6970666 if we wanted to, and we're going to subtract our error, 0.000364088, and then less than or equal to cosine of 0.8, less than or equal to, and this will be our 0.6970666 plus our 0.000364088. So if you want to put that in your calculator, you can pause this video so you can get that interval. And you should have gotten 0.6967025 on this side,